right, y'all, as you can see behind me, I have a question that has a lot more words than the past couple of questions. No graph. This is a little bit different, okay? Now, this is a classic example of how IB can take something, and not just IB, if you're doing AP or GCSE or anything like that, IB can take something that doesn't seem like what we've been studying, and yet somehow it turns out to be connected, all right? What we have here is we have a cylinder, okay? The cylinder is floating vertically in the water. So why is it floating? Well, we know that it's floating because of the buoyant force, right? You should have learned about the buoyant force before, all right? So you have a cylinder that's floating due to the buoyant force, all right? It has a cross-sectional area A, and then the cylinder is, obviously it's floating, so it's partially submerged, okay? Now, when it's at rest, we put a mark right at the surface of the water. And that's actually what we see right here. We put a mark right here at the middle. That is its equilibrium position, right? That's the point at which the force of gravity down on the cylinder is equal to the force of the buoyant force pushing up, right? We could draw a free body diagram for that, but it's pretty straightforward, I think, at that point. We're not going to do that. But force of gravity down, buoyant force of the water pushing up, those two are equal, so we have an equilibrium point right here. Now, we're going to now take the cylinder and we're going to push it vertically downwards so that the mark is a distance x below the surface. Now, what's going to happen? Well, hopefully you're recognizing that now more water has been displaced. The buoyant force depends on how much water has been displaced. If you are now displacing more water, then you now have a greater buoyant force. And so now that nice balance between gravity and buoyant force, that those forces were equal now, isn't the case anymore. Now, the buoyant force is greater, so we're going to have a force upwards that's going to push our cylinder up. Now, the deeper we are, the more the buoyant force is, the stronger the buoyant force is. Now, as it pushes up, it's going to displace less water and the buoyant force will decrease until the mark is right back at the surface of the water again. But at that point, the buoyant force has been pushing up, and it's got some velocity upwards, and so it's actually going to pass the surface of the water, and it's going to continue going up. But as soon as it's going up, then now the force of gravity will be greater than the buoyant force. And so now it's going to start slowing down until it gets as far out of the water as possible. And so now I have the least buoyant force possible because I'm not replacing very much of the water, and gravity will then pull it right back down. Now, hopefully the way I've described it, I'm hoping sounds a little bit familiar. The further we get away from that central mark, the less balanced that the forces are, the greater that the net force is. The deeper you are in the water, the greater the buoyant force is, the greater it is, the restoring force is back to that mark. The more you lift the cylinder out of the water as it's bobbing up and down, the more it goes up, the more that cylinder rises, the less buoyant force you have, and then the stronger the net force downward is because of gravity. Now, the way that they've written the equation here is not the same way that you've seen it before, right? When you've seen buoyant force before, it was rho g v. But they've written it slightly different. The volume of the cylinder is equal to the cross-sectional area, but we don't actually want the volume of the cylinder, we want the volume of the water that's been displaced. So it'll be the surface area of the cylinder multiplied by how deep it is, right? So the net force is going to be balanced, is going to be recognized by this equation right here, where x is how far above or below the water you are. The more down, the bigger the x gets, the deeper you go, the bigger the force will be upwards. The more x goes above, the bigger the force will be downwards. That, my friends, is simple harmonic motion. The force is proportional to the displacement from that center position. You wouldn't think of this as being simple harmonic motion because it's not a spring and it's not a particle going back and forth, it's not a pendulum, but it is. And so that's why they love this type of question, because it connects simple harmonic motion and our buoyant force, which we talked about before. So we're going to use our simple harmonic motion ideas to try to answer this question. Okay, now I actually just answered A for you, right? Outline why the cylinder performs simple harmonic motion. Well, it's because the deeper, and it talks about here, the resultant vertical force on the cylinder is related to this. This is the combination of the force of gravity down and the buoyant force up. Okay, we're not going to go through the proof because that's not asked for here. We could, but it's not asking for that. So we're not going to do that. We're just going to go with this and recognize that the force, or in other words, the acceleration, is proportional to the displacement. That is simple harmonic motion. That's probably enough, simply, right? But you could also go through the process of talking about what I just did. The deeper you go, the greater the buoyant force, and so therefore force and displacement are proportional. Okay? Now, part B says the mass of the cylinder is 118 kilograms, and the cross-sectional area of the cylinder is 2.29 times 10 to the negative 1 meters squared. The density of the water is given. Show that the angular frequency of the oscillation of the cylinder is about 4.4 radians. Holy smokes, it wants me to get angular frequency? Ooh, how am I going to get angular frequency? So angular frequency I'm going to have to get from something that I already know, right? Now, if I look at my equations, and I'm thinking about angular frequency, I'm recognizing that some of these, the only one that I see right off the bat, I see one that has acceleration and position. But I could get acceleration probably from the force if I needed to, but that seems like a lot of work. The other way that I can get angular frequency is from period, right? Period is equal to 2 pi over angular frequency. So T equals 2 pi over omega. Now, do we know the period? No. But we do know, so I guess, again, it looks like we are going to have to go into the force and the acceleration. All right? Okay, let's do it, because we don't know the period. So instead, we're going to use this. That happens sometimes. We think we got it, and then we're like, wait, but I don't know. That doesn't mean we give up. It means we try something else. All right, so I'm going to go with F equals, so now I'm looking at that idea where I'm going to need the angular frequency to get that. I'm going to go back to what I was talking about before. I said, you know, I could use this. It just seems like a lot of work. Well, we're going to have to do the lot of work here. All right, so we know that F equals negative rho A G X. We know that force equals mass times acceleration. So ma equals negative rho A G X. And so from here, we should be able to put the numbers in and solve. Does it give us the mass? Yes, 118 kilograms. So 118 A equals density, the density of the water. Remember, in the buoyancy formula, the density that we need is the density of the fluid that's being displaced. So that's going to be 1.03 times 10 to the third times the cross-sectional area, which is given. That's the 2.29 times 10 to the negative first times G, which is 9.8, times X, which is the displacement, how far it's been pushed down, which is given to me right there. So that's the 0.250, and they were so kind to give it to me in meters. This is in meters squared, this is in kilograms per meters cubed. So everything's given to me in SI. And so now I just need to solve for A. Maybe this won't be quite as bad as I thought. So we'll go 1.03 times 10 to the third times 2.29 times 10 to the negative first times 9.8 times 0.250, And then I'm going to divide by the 118 here. And what I get is 4.897. And so A equals 4 point, whatever the heck I just said, 897 meters per second squared. Now I can use this because I have X, so I can go and it should be negative, right? It is negative there. So I'll go negative 4.897 is equal to omega squared times X. The X again is going to be that 0.250. That's the displacement, that's the amplitude, how far it's been displaced. And so I'll take that number, I'm going to divide by 0.250, and then I'm going to square root it so that I can get omega by itself. And I get 4.42. So omega equals 4.42 radians per second. It's pretty big, it's pretty heavy, so I do expect the oscillations to be somewhat slow, right? So 4.42, I got 4.425. When it comes down to it, it looks like I got 3 sig figs, 3 sig figs, 3 sig figs, 4.4 radians. So if you'll notice, I put one extra digit here. That then shows that it is about 4.4 radians per second. Whew. Got it. Got it. I was a little bit led astray, but like I wanted to show that on purpose to show that sometimes we think that it's too much work, let me try something else, but we just have to come back to that, okay? So we've got A and B. C is determine the maximum kinetic energy of the cylinder, all right? So this actually at this point, SLs, you are done. You don't need to do anything else. You may stop the video because you do not do this piece. HLs, you should be able to now take this angular frequency. Remember, we have the equation we talked about in the first video, which is the total energy equals 1/2 m omega squared x naught squared. And so we will go ahead and do that. I am running out of space a little bit here, so I'm going to erase the work that I have so far because you're watching a video. You can rewind it and you can watch it anytime you want, but I am going to keep my omega there. And so I'm going to use the equation ET equals 1/2 m omega squared x naught squared. And just so that you remember, this ET is the total energy, but if I am looking for the maximum kinetic energy, then I'm looking for the point when all of the energy is kinetic and none of it is potential, none of it is whatever the other energies are that are happening there, gravitational in this case, where it's going up and down and up and down. And so therefore, we can then say, okay, the total or kinetic energy is a max when it's 1/2 times the mass, which was here, 118, times omega squared, which is 4.42 squared, times the displacement squared, which was 250. And so we should be able to plug all that into our calculator. So 0.5 times 118 times 4.42 squared times 0.250 squared. And I expect it should give me something close to about 60. It gives me 72.04. So the total or maximum kinetic energy would be about 72 joules. Everything is in SI units, and so when I get to the end, the answer should be joules. All right? So this is the answer to CI right there. We've determined the maximum kinetic energy. The last thing that it asks us to do is draw on the axes the graph to show how kinetic energy of the cylinder varies with time during one period of oscillation T. So it doesn't give me an axis, so I'm going to go ahead and draw it. I'm just going to draw a little one right here. This should be enough. So this is going to be kinetic energy. This is going to be time. So it does say it was initially pushed down a distance of x. So I push it down. So it's at rest, and then I release it. So I do need to start with my kinetic energy being 0. So it'll be 0, it's starting down, it's going to go up when the mark is at the water, that's going to be my maximum kinetic energy. So it's going to go up to the maximum kinetic energy. It'll pass and go up to the top, and that's where it will stop. And so it'll come back down to have a kinetic energy of 0 again. That's not a full cycle. Remember, we talked about this in a previous video. So therefore, we need to go back down again to where I'm going to have maximum kinetic energy here again. And so I'm going to go up to maximum kinetic energy again until it goes back down to the bottom. So it gets as low as it goes, it slows down, it stops, and then it starts going back up again. But that point right there is where my full says 1 period of oscillation T. So therefore, I can put my period on there. I didn't actually ever calculate the period T, but this would be T, and then the kinetic energy there would be the value of 72 joules that I calculated earlier. All right, that's it. That's this question, and this is an IB type question. SLs, you would very possibly be given parts A and B. HLs, you would be given part C. So I hope that was helpful. That's all I got for today. We'll see you next time.